Emerging Technologies. Let's welcome Federico to give a talk. Federico, please.
Thank you very much for the kind introduction. I hope let's see if this works now. Well, I must say that I'm not a fan of virtual presentations, but this is not the first one I give, and I suppose it won't be the last given the circumstances, and at least we can continue to share results and ideas and so on, despite the pandemic zones. And so I'd like to thank Zhanghua and the other organizers, and I'm excited about this new journal, Smart Mat, and see how it goes. And this is probably a very interesting way of launching a new journal through a series of virtual lectures. So our group studies nanoscale phenomena quite broadly. We're interested in various phenomena that arise when you shrink materials to very small dimensions. Usually new sort of phenomena arise when at least one of the three dimensions is less than 100 nanometers. And we study nanoscale systems quite broadly, as you can see in this overcrowded slide. We study inorganic systems and organic materials, as well as biocompatible materials. And typically the idea is to use nanomaterials as building blocks for different emerging technologies. So in our studies, there's both a fundamental component in which we try to understand very basic phenomena in nanoscale systems, and a more applied component in which we fabricate devices and we test their performance. So the guiding principle behind what we do is to study the role of surfaces and interfaces to determine how these particular parts of a nanomaterial, the surface and interface, determine its functionalities. And that's because in a nanoscale system, contrary to what happens in bulk, the surface to volume ratio is very, very high, or in other words, there's a lot of surface and very little volume. And so the surface, of course, is the part of the material that interfaces with the outer world, and so it plays a very significant role in determining properties. So we take a structure-property relationship viewpoint in the sense that we want to understand how morphology and composition determine the functionalities of a material. And in particular, as I mentioned, in a nanoscale system, so we focus on the surfaces and the interfaces of these systems. And then since we use these as building blocks for emerging technologies, then once we understand the basic concepts of surface property, structure property relationships, then we harness this knowledge to optimize device performance. We work, as mentioned, on several classes of materials today. I will focus on our work in what are called multifunctional materials, which, as the name suggests, are materials that exhibit two or more functions or properties. Now, the main application area that we're interested in today is energy, and that's because we're after the role of energy, and in particular renewable energy technologies, within sustainable development. But what is sustainable development? So here's a definition from the United Nations of sustainable development, and it says meeting the needs of the present without compromising the ability of future generations to meet their own needs. Now, if you look at what's been happening for the past decades, if not longer, everything we've been doing as humans on this planet is not sustainable. And that's why the title of this slide is Sustainable Development, an Oxymoron, or if you want, a contradiction in terms. Putting sustainable and development together is anything but simple. And of course, if we want to attain sustainable development, well, again, according to the United Nations, we have to address the so-called 17 Sustainable Development Goals. And so they're listed here in this slide. Energy is one of them, of course, renewable energy if you want. And I placed it centrally because it's the one that we're interested in, but because also I believe that addressing the energy challenge will directly or indirectly address a lot of other challenges, because addressing the energy challenge, of course, will help make cities sustainable, will help for sustainable development and sustainable economic growth, will help in combating climate change, as well as ending hunger and poverty and reducing inequalities and addressing education. So at the end of the day, all these goals are important, but energy, I think, is central to addressing most of them. Now, let's see in this other slide, the sort of evolution of the kind of energy we've been using over the past few decades and how it's projected for the future decades. So this picture at the left, this is taken from Physics Today about 13 years ago, 2007, and it's remarkable how even after 2007, the projection that they placed in this graph was quite accurate. So this is where we are today in 2020, and these values are quite accurate. So about 80 to 85% of the energy we use worldwide is based on fossil fuels, which is a combination of oil, coal, and natural gas. There's a few percent nuclear, 4 to 5%. Percentage-wise, it's decreasing because fewer and fewer nuclear plants are being built, and overall, on the other hand, energy demand is growing. And then there's a couple of percent hydroelectric. For some reason, hydroelectric is separated from everything else, and everything else is a sort of generic category called biomass and other. So you see, in this graph, in 2007, there wasn't even a category called renewable energies or wind power or geothermal. There was a generic biomass and other, which encompasses all the renewables with the exception of hydroelectric, which is also renewable. And this is quite troublesome. I mean, not only there's like a disproportionate use of fossil fuels, but also the renewables, which are the ones we're supposed to develop and invest in, they obviously, their respective roles are so limited that they're not even broken down into their own percentages. So what are the renewables? So of course, hydroelectric, geothermal, wind power, tidal power, and of course, there's solar energy. And this is the interesting aspect. So we know that every hour of every day, the sun sends towards our planet enough energy to power the whole world for 1 year. And yet, our use of solar energy is extremely limited, very, very, very small. And in 2007, it was less than it is today, but even today, it's not that huge. Most estimates would state about 1 to 2%. So in theory, 1 hour of solar energy could be enough to power the world for 1 year. In practice, we only use about 1 to 2% in our overall breakdown. Now, this is the troublesome aspect of the kinds of the sources of energy we use and so on, and how we face a huge challenge in increasing renewables as opposed to fossil fuels, which of course are finite, a finite resource, and they're highly polluting and therefore responsible for climate change. This is one aspect. But there's this other aspect which has nothing to do with science per se, but actually it tells us that our approach as scientists is extremely limited in what we can actually achieve. So this is world population as a function of time. And so if we go back in time a few hundreds of years or even thousands of years, we find that world population was much, much smaller than it is today, and it was growing very, very slowly. And it's around the 1800s that world population started growing very rapidly. And you can see how this curve, well, it looks a lot like an exponential curve, right? So this curve of world population as a function of time is telling us that pretty much world population has been growing exponentially. And there's a couple of things we should realize when we talk about exponential growth. Well, nothing grows as fast as an exponential. And this growth of population is feeding on energy, and most of the energy we use is non-renewable. In fact, you can see that the population growth started accelerating around the 1800s. And well, you know what? That's exactly the time when we started using fossil fuels on a large scale. So we started with coal, and then, of course, natural gas, and then oil. And now we're at this dependence of 80 to 85%. And because of all the derivative technologies that have come about thanks to fossil fuels, we can call everything that happened in the last 200 years the energy revolution, the medical advances, the ability to grow more food for a rapidly growing population, the ability to travel across continents through flights that take us around the world in about one day, and so on and so forth. So that's the energy revolution, but we have this incredible dependence on fossil fuels. And as long as population grows so fast, there is no technological solution, there is no way that we scientists can come up with new renewable energy technologies that are efficient enough to satisfy the growing demand for energy. So this is part of the challenge. Population growth, which of course, per se, it's not a scientific or technological challenge. It's a political and demographic and economic and sociological challenge. In fact, we've seen, China for a number of decades had this one-child policy, and then a few years ago they decided to relax it to the two-children policy. I was actually in Beijing when the government changed the one-child policy a few years ago. And while the one-child policy has helped to maintain the Chinese, to sort of contain Chinese population to a certain extent, it created a lot of other problems. There is no simple way to deal with population growth, right? So from what I've said, you can see how the energy challenge is not just a scientific or technological challenge. It's much bigger, it's much broader. As such, we decided to address it in a somewhat different way, to take into account other aspects. And so in particular, we reached out to UNESCO, which is one of the UN agencies. It's the United Nations Educational, Scientific, and Cultural Organization. And UNESCO has a program called UNESCO Chairs, which are essentially networks of participating organizations which decide to work together towards some specific societal challenge, usually one or more of the Sustainable Development Goals. And so these organizations will work together and will pool resources to address these challenges and work together towards capacity building, education, transfer of knowledge and technologies, and so on and so forth. And these chairs and networks are supposed to act as think tanks and bridge builders between academia, local communities, research and policy making organizations. So ideally, we want to inform policy decisions and convince those who are in power that it's really essential that we invest more and more in renewable energy technologies and reduce our dependence on fossil fuels. So the main objective of our UNESCO chair is to obtain sustainable energy for all, which is, again, one of the Sustainable Development Goals. And we want to do this through research that is built on sharing knowledge in emerging energy technologies. And so because of UNESCO's emphasis on capacity building in the South, we mostly have partner organizations in the South. We have a lot of collaborators, of course, in China, which is a major player in our activities, but also in many other countries. And basically, we host visiting professors and exchange students. We organize international workshops. And in particular, we train a limited number of PhD students from developing countries, trying to give them an opportunity that they might not have elsewhere. And the title of the chair is Materials and Technologies for Energy Conversion, Saving, and Storage. These are sort of the three broad areas of energy that we're interested in. Today I'll talk out of necessity because of limited time. I'll talk mostly about energy conversion, and in particular our studies related to solar technologies. So you can see here in this slide, this is the solar spectrum. So this is the intensity distribution of solar photons that reach the surface of the Earth every day. And basically the challenge here is to develop materials that are capable of capturing, of harvesting or harnessing as many photons as possible from this distribution intensity and transforming them into another usable form of energy. The most common solar technology, of course, consists in photovoltaics, in which solar photons are converted into electricity. Of course, there's other types of solar technologies converting into, for example, heat or something else. Here, I might as well make a quick stop and remind you of sort of what are the laws of nature in the realm of energy and how they constrain us in what is actually possible. Typically, when given in person, this lecture tends to be interactive. So I ask questions to the audience, and that helps me gauge both their interest and their ability to understand what I'm saying. Since this is a virtual lecture, of course, I cannot ask questions to the audience. So I'll have to hope that you are able to follow and that you're interested. So let me remind you the laws of thermodynamics. The zeroth law of thermodynamics basically tells us that there is a temperature which is called absolute zero, 0 Kelvin, and it's impossible to go lower than this temperature. Then there's the first law of thermodynamics, and this is really about energy, and it's a fundamental law that gives us hope because in 3 words you can state energy is conserved. This is the simplest way, the most elegant way to state the first law of thermodynamics. Energy is conserved. In other words, I can't destroy energy, I can't create energy, I can only transform it from one type to another, according to the first law. And there's a problem here, though. There is a second law of thermodynamics. Now, usually when we study the second law of thermodynamics in our undergraduate courses, whether they are chemistry or physics or material science or some other kind of engineering, well, we speak about entropy. In fact, the second law technically is about entropy, and it tells us that this quantity called entropy, which is a measure of disorder in a closed system, tends to increase. But let's look at the implications of the second law when it comes to energy, because in the end, thermodynamics is about energy. Okay, so if we look at entropy, a measure of disorder, and we associate an entropy to each kind of energy, then we will find that there are qualitative differences between different types of energy. So, for example, heat is very disordered. Therefore, it's a very poor quality type of energy. Electricity is very ordered. Therefore, it's a very high quality kind of energy. What does this mean in practical terms? Well, if I want to transform electricity into heat, my overall efficiency, the amount of energy that I can actually transform from electricity into heat is extremely high. The efficiency is as high as you can possibly imagine, 95, 98%. Some energy is lost. It's not destroyed because the first law still holds, but it's dispersed. You're just not able to transform all of it in a usable form. And that's why it's really the second law that imposes an upper limit on what is possible when creating, when sort of developing new energy technologies. On the contrary, if you want to transform heat into electricity because of the poor quality of heat as a kind of energy, then you will experience huge losses, and basically your efficiency of conversion will be very, very, very low. And mind you, electricity, which is the best form of energy in terms of quality, of its low entropy, well, it basically doesn't exist in nature, right? I mean, excepting lightning bolts, which is not something we can really capture and use. Most of the time, we're trying to transform some form of energy into electricity and then try to store it and then use it later when we need it. And storing energy, of course, is another huge challenge, which we're also working on, but I won't have time to discuss it with you today. Okay, here, this is another interesting concept, which is the Earth at night from a satellite. So here, of course, this is a sort of collection of pictures patched together, different time zones and whatnot, so that you can have a global picture of the Earth at night from a satellite. And first of all, there's a huge waste of energy because obviously there's no need to keep so much lighting on. But secondly, you can see how the availability of energy is not the same for everyone. When you look at the center of South America, well, that's a huge forest, so you can imagine there's not a lot of people living there. So I guess it's okay that there's not a lot of light there because no people, no need for energy. If you look at Australia, most people live on the coast. That's where you have patches of light. That's where the energy is. But look at Africa. As much as there's also in Africa deserts and forests and whatnot, and areas where there's limited population, most of Africa is just dark. And you can actually associate the level of development of a geographical area with how much light there is, excepting, of course, cases where you know that there's a very low population density. So actually, most of India is well developed in terms of accessing energy. And China also, but mostly the eastern part. The western part of China, well, I guess those of you who are originally from China, you won't be surprised to see that the western part of China is much less developed in terms of availability of energy. Now, why did I call this a map of possibilities? Well, that's because if you look at this other map of the world, the same parts of the planet which are dark at night are essentially the ones that have most sunshine during the day. And so in this respect, there's a huge opportunity of deploying solar technologies in these parts of the world, which are the ones that actually need energy more than anyone else, so that there can be a huge societal development and impact, possibly within 1 or 2 generations. And this should also help a lot in addressing climate change. So, of course, there's silicon solar cells, which currently dominate the market in photovoltaics. The cost has gone down. They are quite stable. Solar panels made of silicon can last 20, 30 years. The efficiency is pretty good, 20-something%. order of magnitude, so pretty good overall. There's still some drawbacks. The cost could be lower, of course. That would always be appreciated. But also, making silicon panels is essentially an energy intensive kind of process because you need large vacuum systems which suck up a lot of power, and by their very nature, when these vacuum systems are being used to fabricate solar panels, they obviously, by using energy, they obviously emit a lot of carbon emissions because most sources of energy are based on fossil fuels, and so when you use them, you're actually polluting CO2 into the environment. So we're looking for alternative technologies in which we use earth-abundant materials that are fairly low cost, and for which the fabrication process is low energy intensive. So here we're looking at photoelectrochemical solar cells, which essentially mimic the photosynthesis reaction in plants to a certain extent. And the sort of first type of technology of this kind were dye-sensitized solar cells, originally invented by Michael Gretzel. And now it's a fairly mature technology, almost 30 years, about 30 years later. But of course, they have a limited efficiency. The record in a lab is 14%, which means that you lose when you scale up. And of course, the stability is not that great, certainly not comparable to silicon solar cells that can last a couple of decades. So those are two major challenges that need to be addressed. On the other hand, it's a fairly low-cost technology and quite low in terms of being energy intensive. So in these solar cells, we mostly focus on the photoanode, which is made of a metal oxide, typically a large band gap material, which could be titanium dioxide or zinc oxide or tin oxide. And advantages of these materials take, in particular, titanium dioxide. They're quite inert, resistant to corrosion, non-toxic. They have a high oxidative power, and so on. And however, these materials pretty much all have a large band gap. For example, in the case of titanium dioxide, it's more than 3 eV, which means that titanium dioxide only responds to ultraviolet light. And that is a problem because if you look at the distribution intensity of the solar spectrum, only about 5% of photons coming from the sun are in the ultraviolet region. And so by using simply a metal oxide with large band gap, you would be giving up upfront 90–95%, depending on the material, of course, of solar photons. So you need to sensitize this material with something else that is able to capture photons from other regions of the solar spectrum, visible, infrared, near infrared, and capture them and transform them into charges. Typically, any material that has a band gap can capture a photon. The photon can create an excited state in the band gap. This excited state is called exciton, which has a short lifetime, and then it splits into two charges, an electron hole pair, and then the charges are driven towards electrodes, so that you've succeeded in transforming energy in the form of a photon into charges, into electricity. So in the case of Gretzel's dye-sensitized solar cells, the typical sensitizer are dye molecules. So these are large organic molecules which absorb photons in the visible infrared, near infrared, depending on the molecule. Now here, what we were trying to do is to engineer the photoanode structure by inserting a very small amount of carbon nanomaterials, typically multi-wall carbon nanotubes or graphene. And our hypothesis was that the insertion of this nanomaterial would favor charge transport through the photoanode. And so here you see the sort of photoanode structure, at least how we hypothesize it. It's a mix of the titanium dioxide in our case with the multi-wall carbon nanotubes and the standard N719 dye. These are mixed in ethanol solution, and the amount dispersed of multi-wall carbon nanotubes is really, really small, of the order of 0.03% weight. So really very, very small amount. Basically, you can see here how this this mixed photoanode, this composite photoanode, presents an interesting profile when it comes to its power density output, simply because of the presence of carbon nanotubes. So our sort of record efficiencies for us, for our case, are about 9%, which is certainly not a world record, but quite respectable for this technology. And here you see, so this is in the y-axis, it's J is the current density, and the x-axis is the voltage. So the white squares, the black squares are day one of the standard device, the control. And day 6 is the white square. So you see there's a drop in this curve, quite substantial drop. So if this is y and this is x, then the area under the curve is the power density output of the device. And so there's a drop after only 6 days of almost continuous illumination of the device. On the other hand, if we include carbon nanotubes, on day 1 we get the red circles, and on day 6 we get the white circles. So there's still a drop, but it's actually much, much smaller. So clearly the insertion of the carbon nanotubes improves the stability quite a bit. Now, here you can see that we varied the percentage weight of carbon nanotubes in a fairly broad range, and we analyzed the performance parameters depending on the amount of carbon nanotubes. And so basically, if the amount is too large at 0.25% weight, then the performance parameters are quite bad overall. This is the control, in which there's 0. And then the best case scenario is for 0.01, in which we have a transparent and reflecting anode. The efficiency is 9%. We have a fairly high fill factor and fairly good values of the open circuit voltage and the short circuit current density. Now, the question is, okay, so these are multi-wall carbon nanotubes. Could there be a similar effect from other types of carbon nanomaterials? It could be the morphology or the composition of the nanomaterial that confers these properties. So we fabricated photoanodes using a similar procedure, but replacing the multi-wall carbon nanotubes with graphene. And what's quite surprising is that in the case of graphene, for the same amount, percentage weight of 0.01, we have almost identical performance parameters. So close to 9%, about 74% fill factor, slightly lower open circuit voltage, and slightly higher short circuit current density. So graphene multi-wall carbon nanotubes, both of them enhance the performance parameters. You can optimize by varying the percentage weight, but you get very similar results. And in both cases, part of the effect is to enhance the stability, which is one of the main challenges for these for this technology. Now, of course, those dye molecules are difficult to make. I mean, typically you need advanced expertise in organic synthesis, and we don't have that. And so you either buy them or collaborate with an organic chemist, or you can develop something else that can sensitize your photoanode material. And so here, why is it not advancing? Ah, here it is. Okay, so here the idea is to replace the dye with quantum dots, which are semiconductor nanocrystals that essentially have a size and shape dependent optoelectronic properties. So the band gap in particular is size tunable. They're fairly low cost materials. The processes to make them are low cost and they're low energy intensive. And they're much easier to make than those dyes that I mentioned. So the idea is to sensitize using these quantum dots, for example, titanium dioxide that I mentioned already, to extend the working range into the visible region through quantum dots of suitable materials. And this in principle allows to improve absorption while maintaining good stability and low cost. So in particular, we developed a library of quantum dots specifically looking at core shell and even giant core shell quantum dots. So rather than making quantum dots just of a single phase material, we make a core of some material and a shell of a different material, and this helps us modulate the band gap and other the electronic structure and the optoelectronic properties of the system, so we can really fine-tune the ability of absorbing photons and so on and so forth. So here you see the concept of a quantum dot based photoanode in which the quantum dots used are giant core shell. Giant means that the overall size is huge. Of maybe the whole size of the quantum dot is about 100 nanometers in total. The absorption range is still somewhat limited. It's not as large as we would want it to be. They do have some advantages. They tend to be more stable and less sensitive to the surrounding chemical conditions. The band alignment, particularly looking at the bands that we want to align them to, for example, titanium dioxide, is tunable. Of course, if the shell is too thick, it may affect charge transfer, so there may be other issues that need to be addressed. Now, remember that I talked about solar technologies, so not only photovoltaics. Of course, you can use quantum dots to make quantum dot solar cells, just like you can make dye-sensitized solar cells, and then your output energy is electricity. But obviously, hydrogen is a kind of fuel that a lot of people consider to be the fuel of the future because it's a clean fuel. When you combust hydrogen in a fuel cell, your only byproduct is water. So it does not lead to any carbon emissions. Now, there's three challenges to be addressed in developing a hydrogen economy. One is producing it or generating hydrogen. You can't just dig it out of the ground. Storing hydrogen, H2 is the smallest molecule ever, so how do you efficiently store it? You can liquefy it, but that costs energy, of course, and then you have to maintain it at a low temperature. Using hydrogen in the fuel cell, to combust it, you need a catalyst, an electrocatalyst, usually made of platinum, which is rare and expensive. We mostly work on hydrogen production. And recall that hydrogen is a clean fuel, but the issue is, where do you extract it from? Well, today, most hydrogen is extracted not from water, as you might think, and as we would like, but it's actually extracted from methane, also known as CH4 or natural gas, one of the three fossil fuels. So why is that? Well, because it's much easier to break a CH4 molecule than to break an H2O molecule. And in fact, in the case of water, the reaction is exothermic. So you need more energy to break up the water molecule than what you get back when you combust hydrogen. And so you need some free energy to compensate for that reaction being exothermic. And it turns out that that free energy comes from the sun. Nothing comes for free. Recall the first and especially the second law of thermodynamics. There's always a cost to pay. But anyway, let's say that the energy comes from the sun and we use it to break H2O into oxygen and hydrogen. And we use this making photoanodes for this purpose of metal oxides that are sensitized with quantum dots. I'm going to skip this. I'm going to also, well, briefly mention photoelectrochemical hydrogen production. So the main processes that are involved are light absorption by the semiconducting photoelectrode, separation and transport of photogenerated electron-hole pairs, and these electrons and holes, instead of being collected as electricity, they reach the surface, and that's where the redox reactions for water splitting occur. And so here we used again these giant core shell quantum dots, core made of lead sulfide, shell made of cadmium sulfide. The core shell composition and structure allows us to essentially modulate the energy levels and whatnot, and this optimizes the ability to absorb photons and convert them into charges and split water. So here, back in the day when we first used this concept, we obtained very high values, about 11 milliamps per square centimeter, and overall 110 milliliters per square centimeter per day of hydrogen generation. Now you will notice that the materials we use initially are made of toxic elements like lead and cadmium. So we went through successive cycles of greener materials and greener processes. So essentially from that initial case, we went to copper indium selenide, copper indium sulfide, which are heavy metal free, and they absorb the near infrared. So even though the initial sort of products might contain cadmium or other toxic elements, at the end the final product is heavy metal free, so made of materials that are non-toxic. Of course, there's always a price to pay, so even though these are non-toxic, they perform fairly well, but you can see that the photocurrent density has gone down significantly by a factor of almost 4 to 3.1 milliamps per square centimeter. There's one last technology that I want to share with you when it comes to solar, and it's called luminescent solar concentrators. And this goes back to photovoltaics in a certain sense, because you're transforming solar photons into electricity. But this is a technology which is used specifically for building integrated photovoltaics. So in this case, instead of covering the surface of your building, especially the top, the roof, with solar panels, here you want to use the area of the windows, especially for a high rise. You have a lot of windows and a lot of area that you can use. But of course, if you take traditional silicon panels, they're not transparent. So if you place them in front of your window, you're going to lose in terms of illumination. You might manage to convert a lot of solar energy into electricity, but during the day you would basically lose a lot when it comes to illumination. So the idea here is to cover your window with an organic matrix, and within the organic matrix you have to insert chromophores, which are essentially antennas, and these chromophores are objects that will capture a photon at one wavelength and re-emit it at a different wavelength. And so basically they're embedded in your organic matrix, which is transparent to solar radiation and acts as a waveguide. And so in our case, they're quantum dots. You can use dye molecules or other antennas. Basically, you can absorb and re-emit, and the photons that are re-emitted through the waveguide, they eventually reach a solar cell at one of the edges of this this organic matrix that is placed in front of your window, and that's where you have a standard silicon solar cell, which is high efficiency and long-term stable. And since the area of these solar cells is fairly small, then essentially the overall cost is quite low. So here you can see how we worked on various kinds of chromophores made of these core shell quantum dots. Initially, again, we used these near-infrared quantum dots made of lead sulfide, cadmium sulfide, and because of the core shell structure and composition, we can engineer them to have a large Stokes shift, which is the difference in wavelength between the absorbed photon and the re-emitted photon. And the Stokes shift tends largely to determine the overall effectiveness of these quantum dots. Again, we went through various stages and iterations, starting with these toxic elements, going through other types of quantum dots that are greener and less toxic, heavy metal free. And our latest generation of dots are carbon dots. And here you can see essentially these carbon dots, well, they're pretty green. They are made of earth-abundant materials, mostly earth-abundant elements, mostly carbon, with a little bit of hydrogen, oxygen, and nitrogen, which are the most abundant elements on the planet. And we still obtain a fairly good efficiencies, overall efficiencies for these luminescent solar concentrators. I think I'm going to skip this because we're running late. So I'll just conclude at this point. I shared with you some of our work on nanostructured materials, looking at how these systems exhibit new properties because of size reduction to less than 100 nanometer in at least one of the 3 dimensions. I discussed at length why I believe clean and renewable energy to be central to sustainable development for humans on this planet, and why we're mostly after the energy challenge. And we do this by developing nanomaterials and using them as building blocks for various kinds of energy technologies. So I shared with you some of our work on 3rd generation solar technologies, studying, for example, the stability of dye-sensitized solar cells, and then replacing the dye in these solar cells with quantum dots, looking at photoelectrochemical hydrogen generation, as well as luminescent solar concentrators or solar windows. I want to remind you why it's important to talk about sustainable development, and why it's important that we transmit a sort of healthy planet to future generations. This is an ancient proverb from the people of North America. We do not inherit the earth from our ancestors. We borrow it from our children. And from what I've shared with you, I think you will agree that we are facing an energy crisis. Now, the word crisis has a Greek origin. In the original meaning, it actually means choice, a divergence of paths. And I asked a Chinese colleague, how do you say or write crisis in Chinese? And it turns out to be a composite character in which the first character means danger and the second character means opportunity. So it's again a choice we have to make. And if we continue on the path of fossil fuels, we are clearly in the danger zone. We can instead take this as an opportunity to develop renewable energy technologies and go towards a safer space of sustainable development for humans and all living species on the planet. I'd like to share with you very briefly this this book that I co-authored, and these papers also that I co-authored. These arise from a professional development course that I had originally created almost 20 years ago. It's called Survival Skills for Scientists. And it's essentially advice for young scientists so that they won't make the same mistakes that we made in our career. And the book was quite successful. It was even translated into Japanese. So you can see here, there's a version of my book I can't even read. I don't know if it's accurate or not, but people seem to like it. So I guess that's a good sign. And I should also mention I'm one of the associate editors of Journal of Materials Chemistry C. Our latest impact factor for 2019 is slightly above 7 for those of you who believe in this kind of metric. The journal essentially focuses on materials chemistry and their application in these specific areas, which are sensors, optics, electronics, optoelectronics, magnetism, and whatnot. if you're interested in, especially if you're interested in writing a review article for our journal, please contact me by email and we can discuss this. And last but not least, I owe a debt of gratitude to the funding agencies that support us. Provincial funding agencies in Quebec and from the federal government of Canada. And of course, also I owe a debt of gratitude to collaborators from all over the world. I counted recently that I've co-authored publications with scientists from 36 different countries, and in particular to the trainees, the graduate students, the postdocs, the visitors that come and work with us. I've had over 160, and they come from 42 different countries, and 20 of my alumni are now themselves professors in 11 different countries. And you can see this is one of our favorite activities, a water fight in the backyard of our center. So this is one of our extracurricular activities that we engage in typically during the summer. During the winter, it would more likely be a snow fight because of very low temperatures that we have here in Quebec. Thank you very much for your attention.
Hey, thank you very much for the wonderful talk. It is our pleasure to invite you as the guest speaker in SmartMat lecture. I'm Chen Xi, the managing editor of SmartMat. We're going to start the Q&A section. I will ask the question on behalf of the audience. The questions are collected from the live broadcasting platforms like Bilibili, Baidu Live, YouTube, and Facebook. So during the time that our staff is working on questions, I would like to briefly introduce our journal. SmartMat is newly launched open access journal by Tianjin University and Weili. The first issue will be published in December 2020. The editors-in-chief are Professor Wenping Hu from Tianjin University and Professor Hua Zhang from City University of Hong Kong. Our journal mainly focuses on the topics of optoelectronic, biomedical, stimuli responsive, self-healing, and nanomaterials for next-generation sensor, actuator, energy harvesting, wearable device, and drug delivery system. Now we're open for submission. Please visit our website and WeChat official account for more information. Now I will go back to the Q&A section. The first question is, what is the current challenge and the perspective on solar technologies?
Well, solar technologies are doing quite well. As mentioned, silicon dominates the market, and the cost has gone down and they're being used more and more. I guess part of the challenge is to make them even more cost effective comparatively to fossil fuels. And then if you want to replace silicon, not so much because of cost or stability potential issues, but mostly because it's high energy intensive, then of course you have to use materials and improve their overall performance in terms of stability and efficiency. So I think silicon could actually have a much larger share of the energy market, silicon solar panels. But recall what I mentioned earlier about policy. There has to be a decision, a willingness from governments to actually invest in renewables, and you know, fossil fuels for the longest time have been subsidized. It's time to stop subsidizing fossil fuels and instead subsidizing renewables, both research in renewables to make them more effective and also just subsidizing the adoption of renewables by private consumers. So I think these are some of the challenges, and partly scientific, but also very much related to sort of economics and politics and so on.
Thank you. And the second question is, what about the heterojunction-based photoanode for quantum dots as compared to core shell structure?
Sure. I mean, there's many ways to use quantum dots in a solar technology. I mean, we've been using core shell. You can use other architectures, and you can use other sort of device concepts, and at the end of the day, you're going to face pretty much the same challenges all the time. It can be the cost, and it can be the stability and the efficiency. Those are the three main challenges. So some people have demonstrated very good efficiencies with heterojunction systems. They tend to have other drawbacks. So as usual, there's no perfect solution and there's no free lunch. So as I showed earlier, whenever you change some parameter, you may gain somewhere and you're very likely to lose somewhere else. So that's at some point you have to make choices based on the trade-off and what you find to be acceptable.
Okay, thank you. The third question is, what is the future development for the luminescent solar concentrators?
Well, I think luminescent solar concentrators have huge potential because they're fairly low cost and they can actually power a significant portion of a building. So I think it's a matter now of well, I guess there are some commercial products, but it's a matter of more companies trying their luck and commercializing these, and that might be quite a challenge in its own right, especially during a pandemic, for people to start companies and making a bet that it will all work out. But I think the materials and the technology for these solar concentrators as solar windows, I think it's mature enough that we could enter a phase of commercial products that can be integrated into buildings and actually power most of the building's activities using these solar windows.
So your understanding for Weiji is very interesting. So could you please give some suggestions on this? I think it's about the energy crisis. What is the opportunity and what is the danger?
Oh, you mean about this one? Well, the danger, of course, is if we continue using fossil fuels, then first of all, they're a finite resource, so at some point we will run out. And secondly, we're polluting the environment, which means climate change, global warming, and so on. So the population, and we are destroying the planet through climate change and global warming. The opportunity is, okay, so we realize that what we've been doing so far is dangerous, so let's do something else. Let's take this as an opportunity to change course and to decrease our reliance on fossil fuels, phase them out eventually, and invest more and more in renewable energy technologies. And that's the opportunity that can lead us on a path towards sustainable development.
So the next question is about UNESCO. You will mention that there is program for PhD students or young researchers. Could you please share more information about the program?
Sure. So basically, where is it? Okay, here it is. So every year we host visiting professors and visiting students, and we organize workshops sort of as networking events and to develop collaborations. And every year we also have a limited number of scholarships for PhD students from the South. And this year we just closed the deadline for our call for PhD scholarships, but since we didn't receive many applications, Actually, we might extend the deadline. I'm not sure yet, but there might be a possibility. If not, usually we launch this competition every year. So these are scholarships to work mostly here in Canada, but typically in collaboration with an organization in the South. They're 4-year scholarships valued at $30,000 Canadian each, and typically there's 2 scholarships per year that we offer through this program. We've had students from various different countries, a few from China, also from Nigeria, Tanzania, and Mexico, Iran, and Ghana as well. Yeah.
So is there any specific requirements for the students or like application?
Well, sure. I mean, I don't know if there's a way to circulate by email the call. If there is, I can send you the sort of ad that we use. But essentially, the requirements are to have a very good academic profile, and then interest in working on renewable energy technologies, a sort of vision statement in that respect, and also willingness to work with us, but also a kind of commitment to later on go back to their own country or to another developing region so that they can transfer the knowledge and technological know-how that they develop while working with us.
Okay, thank you. And so this is the last question. So please let's thank Prof. Rosei for the wonderful talk again. Thank you so much and welcome to Summit to SmartNet. 感谢科研云能源学人
Thank you.
感谢科研云能源学人的大力支持。
Thank you.
9月25日上午9点，我们请到了来自德雷塞尔大学的 Yuri Gogosi 教授给大家带来精彩的演讲。此次讲座会有转发有奖活动，送出100元购物卡，敬请各位持续关注 SmartNet。Thank you so much. Thank you.
谢谢。